correct, because I've actually said this in building codes committees and standards committees. It's like condensation's harmless. It's just water. It's that prolonged time factor in there when it's constantly wet, materials are constantly damp. They may not be condensation. It may just be damp building materials, because when building materials get cold, they start to absorb more moisture into the pores. So you've got these damp building materials creating higher humidity surrounding that building material. When you get high humidity above 70, 80% for a prolonged period of time, then you potentially induce mold growth.
Well, Jesse, it's super exciting to have you here on the Undercover Architect podcast. You're somebody I've been wanting to speak to over, in person, on Zoom, online for a very long time. You are a leader in the industry. You have a significant wealth of knowledge and experience about the topics that we're going to be talking about today. And so it's really awesome to have you here. And for those of in the Undercover Architect community that might not have heard from you or met you, to be hearing from you here for the first time. So I'm wondering, before we jump into what we're going to be talking about, if you can just give us a little bit of background about yourself and how you got into the work that you're doing these days.
Okay. How far back do you want to go? I guess if you go back to, well, I'll start at the beginning. I grew up in Sydney, but my dad was a builder. So I spent a bit of time on building sites when I was younger, helping out, learning how stud frames go together and timber framing and all that sort of stuff, and putting plasterboard on walls, all that sort of fun stuff. But I actually did engineering at uni. So I went and did a degree in photovoltaics and solar energy at University of New South Wales. And I was always...
That's where I went. So
yeah,
that's where I did my architecture degrry. It was great for that kind of study, I can imagine. So with the amount of research they had there. Yeah,
so the photovoltaics thing was led, they were leaders in the field at University of New South Wales. So that was a bit of the progressive thinking side of things. Where's the world going? What do we need? Solar panels, solar energy is going to be the next big thing. So I did that. Pretty naive, I guess, because I thought 3 years was a long time. 4 years for a university degree is a long time, and the industry would be massive and booming. But when I got out of there, it wasn't as big, and there weren't as many jobs as I thought there would be. Much different now, 20 odd years later. But I ended up then going into consulting, so consulting on sustainable building design. And that was about, energy efficiency and a lot of glass talk and, performance glazing and how to stop buildings overheating and using too much cooling load. Did that for a few years and ended up transitioning into the building products sector, which I actually loved a lot because it became more practical. As in, how do you assemble buildings to actually get them to work? And that practical side of how to insulate buildings properly, because I was working for a building products group that did insulation, and how to insulate the building properly. And then also, well, is insulation always just a good thing? And marketing departments will never tell the negative side of certain aspects of the products they sell. But if you don't insulate a building properly, then you can end up creating perverse outcomes, or as the regulators like to call it, unintended consequences. And it's not that insulation is a bad thing, it's just if you don't know what you're doing, you can end up with unintended consequences. And those unintended consequences happen to be moisture, condensation, and perverse outcomes like mold in buildings. Particularly when you start to then go, well, how do we make super airtight buildings that are super energy efficient and well insulated, and we don't care much about moisture or forget about it? Then you potentially create big problems. And that's what I was doing in the building products group. So I was looking at the building science side of things. So it's that sustainability bent, which is insulating buildings is a good thing, yes, tick. But how do we do it really well so that we don't create unintended consequences on unhealthy buildings? So from there, I ended up where I am now, which is talking about moisture and mold in buildings. And I ended up in this rabbit hole that I'm still stuck in.
And it's a rabbit hole that you're very well versed in. So
Yeah, and there's kind of, the engineering code of ethics. If you see something that is going to harm people, then you have to try and solve it. And that was, I was lobbying for air tightness in the building code, things better, more energy efficiency. And it's like, well, hang on, maybe we better work out how to do it properly, and then we can push that lever or pull that lever as hard as we want on energy efficiency.
Fantastic. Thank you for that run through. I was listening to another interview, I think, that you'd done on the Sustainable Builders Yak, and you said that you grew up in a house where the bedroom had the exposed studs and they were your shelves. And I had to laugh because that's exactly what my son's bedroom looks like.
Yeah, absolutely. And I think that's all builders' houses, which are half built, because they do it in their spare time. So my dad was a builder, and it was, I've got a few weeks, I'll put a new wall in, or put some plasterboard on here. But we just had little noggins that we used to keep all our toys on. All the Lego and everything that we used to make was sitting on the exposed noggins.
Yeah, very familiar. So now I'm wondering if we can dive into sort of a building science 101 and just going back to basics for people to understand. The undercover architect community, I find, has a varying range of knowledge in terms of some, all across understanding air tightness, insulation, condensation management, those kinds of things, right through to people who it's their first foray into this. They're, not even sure whether they can question how the builder might be building something or how something might be designed. So, why do we need to understand moisture and vapor and how it moves through a building envelope? And, what's important to know about this from, working with porous and non-porous materials, and what this can do to set up not only the building's longevity, but then also the health of the occupants?
Yeah. Okay.
It's a big question, I know, but yeah.
That's what I mean, the rabbit hole that I never came out of. So it all, like I said in the intro, stems back to energy efficiency. We start to change the dynamics of a building when the government turns around and pulls a massive lever and says you must insulate your building and keep insulated more and more every few years. Or actually, I should say they haven't really cranked it much for the last 10 years, but it did increase from nothing to a decent amount of insulation. Then you change the dynamics of the building. You're retaining energy, heat, in the building, or blocking the heat out of the building. But when you start to change the dynamics of that building envelope, if one side is going to stay warmer, the other side is going to get colder because you're retaining that energy. So the cold surface then becomes a potential risk of high humidity, condensation, mold growth. And then you start talking about porosity of building materials, which I've been talking about a lot, but porosity and also vapor permeability. And porous materials, which is stone, masonry, timber, wood fiber, anything that has pores in it, water vapor can generally get through, not necessarily, but generally get through. It's when you start to then go to non-porous building materials like glass, aluminium, metals, then when they get cold, they condense water on them. And that becomes really obvious when you look at the old single glazed windows in houses. And probably most parts of Australia, people would experience condensation on single glazing during the winter. And that's I guess the early signs of, hey, maybe there's something wrong here, or maybe there's something that could be done better. So yeah, I don't know if I've answered your question yet.
Yeah, no, I think
talking
you
about
have.
porous,
Well,
non-porous building materials. And yes.
Yeah, well, and thinking about this from climate to climate. So I know lots of people, for example, I put up a post recently on Instagram and Facebook. We have a dehumidifier going in my son's room in particular, pretty much 24/7. The house that I live in is a weatherboard house that was built in the 1980s, but it was built without any insulation in it. So a bit of insulation in the ceiling that, of course, is that glass bat that, isn't doing a lot because it's sagged under its own weight over the years. But his dehumidifier will pull out, on a humid day in the middle of winter, will pull sort of 6 to 7 litres, sometimes 8 litres out of the air overnight. And a lot of people got in touch with me and said, well, we don't need to worry about that because we live in Adelaide, or, this is not something that we need to be concerned about because of where we are. So, How do you see people misunderstanding how this can perform and work in different climates, and then potentially just discarding condensation management as something that they need to think about versus making it relevant for their climate and understanding that it might still impact them in some way, shape, or form?
Yeah, it's something that always comes up, which is, this is Australia. Doesn't matter. We just do our own thing. No, that's a European problem, North American problem, US problem, but this is Australia. And for some reason, we don't have to worry about anything. And to some extent, people are right. If you're living in a really old, super air leaky house, then you might not have to worry. But because all the air is just literally letting all the water vapor get out of the house, but you're not going to have a comfortable house and it's not going to be energy efficient. Well, it could be energy efficient if you just don't heat it and you just don't cool it. But if you don't heat it, then you got to worry about, well, how healthy you're keeping yourself in winter. So then it's a crossover with, well, how do we actually keep our house in a healthy climate condition? And then we're going to be air sealing it to help us do that in an energy efficient manner. And then moisture comes into the equation because we're starting to air seal and insulate. And then all of a sudden, the humidity and the moisture vapor that people, water vapor that people are giving off is increasing the humidity indoors. Then you have to worry about moisture. And I mean, not worry, I guess, as such, but you have to design for it. And if you don't design for it and just say she'll be right, then it's quite easily you can create a perverse outcome. So all the stuff around the building physics and the building science and air tightness always falls at the heart of the whole discussion. But people, you either see it, a lot of people see it as a negative thing. I don't know where that's flipping. Hopefully it is flipping, because air tightness is actually, yes, it can create problems, but it's also the solution to the problem. Because once you start building semi-airtight buildings and you get this water vapor accumulation, entrapment, sort of indoor humidity increasing, the only way to actually control where that water vapor goes, potentially accidentally, into dark, damp cavities in your construction, is to make your building more airtight so that it doesn't accidentally flow into your cavities. So you start making the building more airtight and really controlling where you want that water vapor to go or not to go. And generally you want to let it go or control where it goes through fans and air distribution systems. So
into areas where they can then be dried out
to be
over
ventilated.
time. Yeah, to be ventilated. Yeah.
Pretty much. Yeah. So you have a dedicated exhaust fan that carries all the moisture out. But if you've got super air leaky buildings or semi-air leaky buildings, then that moisture just goes up into your roof cavities or into your wall cavities or wherever and finds a cold surface and goes, oh, this looks pretty comfortable, and sets on the cold surface and starts to go moldy.
Yeah. Yeah. And that's the thing I think people don't understand, is that condensation in and of itself isn't the bad thing. It's prolonged condensation, and what it then does under certain circumstances to be able to then grow into mold and degrade buildings and cause problems with people's health, and particularly when it's in areas that aren't visible day to day, and what then can be happening behind the walls and the roof of your home.
Correct. And that's absolutely correct, because I've actually said this in building codes committees and standards committees. It's like, condensation's harmless. It's just water. It's that prolonged time factor in there when it's constantly wet, materials are constantly damp. They may not be condensation. It may just be damp building materials, because when building materials get cold, they start to absorb more moisture into the pores. So you've got these damp building materials creating higher humidity surrounding that building material. When you get higher humidity above 70, 80% for prolonged period of time, then you potentially induce mold growth. And that's a potential problem that happens even when you don't have liquid condensate occurring. So it can become quite a complex issue, but it's well researched, and there are definitely solutions out there in the market. But it comes back to design. But more importantly, how you construct the building, because it's a quality of construction necessary to get this all to work. And it's not just slapping things together and adding on another bedroom and increasing the floor space by 20 meters squared and going, yeah, great, I've got more floor space. It's about how do you actually put these systems together? How do you put the roofs together? What are the material layers you're using? What are these insulation types? How do you get air in and out of these systems to remove moisture if necessary? All this is super important details that we need to consider.
Yeah, fantastic. And we're going to dive into some of those details, because I think that it's worth alerting the Undercover Architect community that Pro Clima released an incredible report. It's called An Australian-Based Study on Air Tightness and Moisture Management. It's an amazing report. It's also a chunky report. So it's got a lot of information in it, a lot of data in it, over 136 pages.
Yeah.
And you are one of the key authors. What actually prompted Pro Clima, because this would have been a big investment of time, energy, resources, and it spans over, there's years of data in it. What actually prompted Pro Clima to go through to the effort of compiling all of this together in this kind of, earmarked report that's just, sort of almost draws a line in the sand, I think. And then how did you actually go about it? Because I can imagine it was a massive undertaking.
That's thanks for the question. Because I guess you're absolutely right. It was a massive undertaking. It's something Pro Clima does all around the world. So it's not just an Australia study. There's a New Zealand study. There's an Irish study. There's you look in online and you'll find them. But it's a bit stems back to that what I said earlier. But this is Australia. So you need to go, well, okay, this is Australia. Let's take Australia. Let's do the analysis. Let's work out these systems that we're promoting as Pro Clima. Why do they work or why don't they work? And some of our really standard generic systems that we use in cold parts of the world, they don't actually work in Darwin. And openly say that, but that's because this is Australia, but that's the tropics. And the tropics and that really hot, humid part of Australia does need to be addressed differently. And it's not the standard off-the-shelf Pro Clima system that works, but the standard off-the-shelf Pro Clima system does work for the majority of Australia. And I'm talking about, I think we might get into it, but, external membranes on the outside of the timber frame structures and air tightness, vapor control layers on the inside of the structures actually work for the majority of Australia and help deliver construction systems that don't get wet from rain, don't get water leaks into them, and let the construction systems dry out. So that's why the study came about, because it's like, well, we have to take the whole of Australia and we have to address every part of Australia and tell people why it works or why it doesn't work. And I mean, by the time it took 4 years, to probably a good part of 4 years to get to the end of it. And that's, a lot of the work done in the evenings and a lot of late night meetings with Germany and, toing and throwing on specific details and, the correctness of all the points we're putting in. Are we absolutely right? So there was a lot of thought that went into it, a lot of meetings, a lot of time, a lot of graphics, a lot of animations to try and get those concepts across as clearly and concisely as we can. But like you said, there's still a massive chunk of information. But I think one of the really important parts in that study was one of the later chapters, which was what are the builders around Australia actually doing? And they're building this stuff. They're building the Pro Clima systems to deliver better, more healthy, more durable, more energy efficient buildings. And it's always, I guess, in Australia, people in the construction industry, a lot of people never want to be first. They always want to be second. But the good thing is there are a lot of builders out there already doing this stuff. And it does work in Australia. And yeah, it's been done all over Australia. And that just a lot of the images and a lot of that was taken from content out in the World Wide Web, social media, basically.
Fantastic. Yeah, I highly recommend that that homeowners check it out. Undercover Architect audience really does like to get itself informed, and so this is an opportunity. All it'll cost you is an email address. It's it's available on the Pro Clima website, so I'll pop that link in the resources. And I think at the very least, alerting your professional team to it so that they can have a look at it. It does go through a lot of, there's even the glossary of terms at the front is a really fantastic and handy kind of tool to have to sort of understand some of these things. And I wanted to dive into that because it says, and I'm going to read this out. The report begins by stating that this study outlines construction solutions to achieve low energy, healthy and durable housing for future generations. A desktop analysis using Woofy Pro software shows that in space-conditioned housing, the incorporation of intelligent air barriers, or IABs, on the inside of the framed wall assemblies in Australia will almost completely eliminate the risk of mould within walls in all climates except the tropics. And then you go on to talk about what to do in the tropics as well.
Yeah.
So can we just talk through some of these acronyms? So there's IABs, there's obviously VPMs, there's which are, vapor permeable membranes, there's weather resistant barriers, WRBs. It's a lot for homeowners to kind of navigate.
Yeah.
How do these barriers work, and how are they different to foil sarking and, the blue wrap that everybody, or green wrap, depending on what state you're in, that everybody is so used to seeing? And, in terms of also understanding, because the National Construction Code then refers to pliable building membranes, so it uses another terminology. How do homeowners need to understand these different acronyms, these different products, and how it differs to what we've been using previously?
Yeah, and I mean, it's understanding acronyms is part of what makes you an expert, right? People dream them up just so that people don't know what you're talking about, and you need to do 3 years of study to work out what the acronyms mean. But ultimately, where do you want to start? And which the WRB on the outside, the IAB on the inside, WRB on the outside. So weather resistive barrier is what we were calling it, or what we are calling it. But this varies around the world. So the weather resistive barrier is what sits on the outside of the, let's call it an insulated timber stud frame. And that on the outside of that WRB, there's going to be a cladding, a fibre cement, a weatherboard, a brick veneer, whatever it might be. But that is literally a sarking. It's a sarking type material. The issue that we had with sarking and sarking type materials is that there's a legacy. The legacy there of the history of use in Australia is sarking is aluminium foil that you buy in Bunnings. And that's not what we want to be associated with. So weather resistive barrier is a term that was used in the US mainly, but sometimes it's also a water resistive barrier. But whatever you define it as, we actually chose the term weather for a specific reason, because those membranes on the outside, it's not just water that you got to prevent getting into your building. There's wind pressure on the outside of the cladding materials or the walls. That wind pressure is what forces water into the system. The membranes have to withstand that wind and that water getting in the construction system. They also have to withstand, or maybe during the construction process, is exposed to UV. It's exposed to UV, it's part of the weather, so it's also got to resist that UV to a certain extent. And that's part of the durability story around Pro Clima's membranes, because they're some of the most durable membranes on the market as well. And then also you have high temperatures, summer in Australia. Cladding, lightweight cladding systems, even metal cladding systems, if you're going for colour bond or something like that, can get extremely hot. And then the membranes have to withstand that heat as well. So that weather resistive is all those elements, but it's there to stop water getting into the insulated timber structures. So that's the outside, weather resistive barrier. And weather contains, the term weather is all those aspects I talk about.
And it's resistive, because resistant.
Yeah,
so there's a difference in that as well.
Yeah, so weather resistive, and this was again stolen from all the intellectuals in the US as well, because I'm sure they debated this in committees and sitting around the campfire for a long time, because resistive implies that you're never going to have perfection. If it's just a weather barrier, full stop, end of story, you're implying that it's perfect. But the point is that no matter how hard we try as designers, as builders, to get it absolutely weather tight, you always might end up with some water leaking into your structure. And if that happens, you need to make sure that all the layers around that structure are vapor permeable to allow it to dry out. And that's part of the story as well. So the resistive is actually a really important word in that term. And the barrier part is, well, that's what we're striving to get, barrier. But like I said, perfection is impossible. So let's just go for as close to perfection as we can get.
Awesome. And then the vapor permeable membrane, or the VPM?
Yeah, so vapor permeable membranes. So is that in the glossary, is it?
No, well, I think that's another way that these layers get talked about in
Yeah,
terms of being whether they're vapor permeable
or vapor barriers.
or vapor barriers.
Yeah,
So in terms of people understanding that,
yeah,
and again, how that might, because I think that some builders who aren't informed about this would
yeah,
argue that a perforated foil sarking that's just had
yeah.
holes stabbed in it with
Yeah.
nails, or has come perforated, would be considered a vapor permeable membrane. So how does that differ as well from the foil sarkings that that we've previously used?
Yeah, yeah. Okay. So vapor permeable, technically it is a vapor permeable membrane if you've got holes in a vapor barrier. So holes in a sheet of aluminium becomes vapor permeable, yes. But it's missing that weather resistive part because the water is going to go straight through the holes. So you get any wind pressure, any water onto that membrane under in a wall system, for example, then the water is going to go straight through it. The wind pressure drives the water straight through the holes. The Australian standard doesn't let you use those perforated membranes on a roof system, for example, because obviously gravity is just going to drain the water straight through the holes. So VPM, vapor permeable membrane, often gets thrown around, and that probably stems back to the Australian standard 4200 Part 1, which has certain classifications around membranes. And this was opened up in 2017. I was actually on that standards committee, and the classifications of the membranes are class 1 to class 4. Class 1 and 2 are vapor barriers, and these have existed forever in Australia, and that's the aluminium foil type membranes. But then class 3 and class 4 start getting into membranes that allow water vapor to pass through them. And the aluminium foils with holes in them would technically fall somewhere in that class 3, class 4. But they've got that major problem of water holdout and being a water barrier and protection against driving rain ingress. So that's what a VPM is, something that allows water vapor to pass through it.
Gotcha. I think it's interesting kind of to mention as well. I think what I've noticed in the difference between how people think about construction systems in Australia versus, in places like Europe and America, particularly from a building science point of view, is that there's an expectation in Australia that in a timber framed lightweight wall that the cladding is doing the waterproofing of the wall.
Yeah.
And yet in the States and in other locations, there's an expectation that you still need a line of weather resistance behind the line of the cladding, and that the cladding's not going to do 100% of the job of making the wall weather resistant. And so it can be quite interesting for people to kind of contend. I noticed that there's a mindset shift for people building in Australia when we're so used to that being, a brick veneer or a FC wall or a weatherboard wall. The expectation is, well, why do I need this layer inside my wall when the cladding's doing, all of the jobs of keeping the wall dry?
And that's, it's a massive misconception of how weatherproofing how weatherproofing in wall systems actually works. And I've been having this discussion at a building codes level as well, because it's like, why are you specifying in the building code systems like lightweight clad walls need to do this, or brick veneer walls need to do this? It's not the cladding type that even matters. You need to take it back and say every construction system in this country, in every climate zone, needs to have a weather resistant barrier. You need to have that on the drawings, and you need to be able to point that to that when it's installed. And it's not the cladding, it's the layer that sits behind the cladding. Then you've got a chance of making that system weather tight. There are some construction wall systems on the market that try and seal the cladding to the extent that the cladding itself is the weather tight layer. There's some major problems with that. And the thing is that when you start to caulk cladding, let's take fibre cement, for example, 6mm fibre cement, put on the wall, caulk all the joints or seal them all up, eventually they're going to crack. They're going to crack on the joints, they're going to crack around the windows and how you connect it into the windows. When it cracks up, then you get rain on that cladding with some wind pressure, just a small amount of wind pressure, it drives water straight through all those failed joints. And that gets into the wall system. And then how's it going to dry out? Because you've got no ventilation. So then if you get too much water in there, then the whole system just starts to rot. And what I'm describing here is something that you may have heard before, which is the New Zealand leaky building crisis. And that essentially is what caused it. You put all your eggs in one basket, and that basket is the render coat, or the basket is the paint coating on the outside of the fibre cement. You've got a massive problem when that cracks up. And I always ask the question, what's the most vapor permeable membrane you can get? Do you know what it is?
No.
Nothing. It's air. You just take the membrane out and the water vapor can go straight. Oh, but hang on. How am I going to weatherproof my building if I've got no membrane in there?
Yeah.
So now you've got this double-edged sword. I need to put a membrane in, but I need that membrane to be as vapor permeable as possible to allow the water vapor out. But also, if I drive the vapor permeability of the membrane too high, then I start to compromise the durability of that membrane. Because you can make them super vapor permeable, and have done this around the world, but those super vapor permeable membranes had massive durability issues, which then in Germany led to failures of those membranes, which then led to water ingress or failure of the weatherproofing systems, which is actually worse than the condensation problem. But so this is the double-edged sword.